Bueno, bienvenidos a todos al Community Tour 2022 del EAUC. Este año nuestro evento, obviamente, al ser virtual, va a ocupar 5 días. Tenemos un montón de charlas, 44 charlas, 33 presentadores. Se pueden registrar a las que ya pasaron, si es que se la perdieron. Pueden registrarse a las nuevas que faltan del día de hoy y las del día de mañana. Por supuesto que queremos, por lo menos Kai y mí, queremos agradecer a los grupos de usuarios de ADC que han hecho parte de este esfuerzo nuevamente por tener el tour en vivo. Y para la charla de hoy de Kai, tenemos que se trata de Average Active Session Prediction Using Deep Learning Network, un tema que a mí me encanta, pero que no he tenido todavía tiempo de probarlo. Pueden utilizar el chat si quieren hacer alguna pregunta. El simbolito en el chat que permite hacer la traducción automática, pero si quieren, bueno, pueden escribir en castellano y luego yo le traduzco acá la consulta al final de la charla. Bueno, sin más introducción, creo que Pera lo conoce todo el mundo, es un experto en el tema de performance de la base. Así que, sin más introducción, agradecerles que estén presentes acá y los dejo en nombre del ELC con Craig for your presentation.
All right.
Yeah.
Good morning. Can you hear me and see my screen?
Good. The screen is not ready yet.
Oh, stop. You do not see it. Can you see my screen? Presentation? You cannot?
Not yet.
It says pause sharing. Okay, let's try again. I wonder why not. Okay. Well, let's see. It says that it's sharing on my screen. Okay, let me stop sharing and reshare it. Let's do that. Okay. Share screen. It's working on it. Okay, let's try. There we go. Wow, that took a long time. Here we go. Can you see it now?
Not yet. It's show loading.
I don't know what else to do.
I close this.
Okay, so let me start over. So I will exit and come back in.
Okay.
Okay, all right. Don't go anywhere. Okay,
Yeah.
I'm going to exit Chrome here. So we're going to start over. Can you hear me?
Yeah.
Okay. Now let me try and share my screen.
Second time.
Here we go. Okay. Screen 1. Is it working? You still cannot see my screen.
Not yet.
It says it's loading. Gosh. All right. Well, then, all right, let me try. I'm going to have to try another browser. I'll try Safari. It was working before. That's what is first.
Yeah. First time was perfect.
All right. So I'm going to exit Chrome again. Okay. Can you hear me?
Yeah.
You can't. Okay. And you can see me?
Yeah.
Okay. Should we try the screen share? Let me get rid of yours. Here we go. Okay, here we go. That was faster. Can you see it? Yeah, use Zoom. Yeah. I don't know. I don't know what to do.
Yeah. It's okay.
You can see my screen?
Yeah.
Wow. That was weird.
Yeah.
Okay. Yeah. Hold on. Let me get this out of the way here. That was exhausting. I'm tired now. Okay, well, let's get started. All right. So first of all, welcome. I'm very happy to be here. And I hope this is a very beneficial presentation for you all. I asked for a longer time slot because there is a lot of content. And I wanted to make sure there was plenty of time. I realize that English is not your first language, and I don't speak Spanish. So I will try and use few words that are good words. So a couple things before we get started. Behind me, those are birds. We have birds in my office here, and that's kind of you're going to hear them make some noises, so that's okay. Second thing, at my house, there is an electrician coming today. He is not supposed to turn off the power to my Wi-Fi, but if he does, I will get back on in 5 minutes, something like that. Okay. The third thing, I will present for about 40 minutes, and then we'll take a quick break, and then I will finish up, okay, because this will be a longer presentation. So, okay, let's get started. So today, we're going to talk about making predictions of the next average active session value. Now we're going to, the data we will use will be sysmetric data. This is, and it is AWR sysmetric data that we will be using. The type of machine learning models and algorithms that we will be using are called deep learning, and they're based on neural networks. So, and I will explain all of that. Well, I will do my best to explain all of that. Okay. So this presentation is about half of me talking with slides, PowerPoint. The other half will be doing a demonstration. So the very specific machine learning topics, I will be using what's called a notebook, not the PowerPoint slides. So that's how things will be organized. So what you are looking at, that is the result of the project that we will be creating. Actually, the project is already created. I will just work through it with you. Even now, you can download the presentation slides and the project from my website. Okay. And when we get near the end, well, you just go to www.orapub.com and sign in and just go to the presentations. And right now, my presentation is at the very top, so you will see it. Okay. All right. We can do machine learning. Okay. If you get frustrated, just remember at the core, it is all about recognizing patterns. All right. And if you can tell yourself that, then you can just kind of calm down, and then we can continue learning. But it's different for DBAs, but you can do it. Okay. So very quickly about myself, I am OraclePub's founder, along with my wife, Katrina, and we are both employed by Viscosity right now. I have the best title I have ever had, called I am the Applied AI Scientist. And what does it say? Oh, I am a longtime Oracle DBA. Yeah, and I focus on predictive analytics, machine learning, and Oracle performance tuning. Nearly all of my performance research is on my blog, with just a little bit of machine learning right now. I am the author of 2 books, and I do a lot of conference speaking and teaching and mentoring. I'm an Oracle ACE director, which is very nice. And I'm on the board of the Utah Oracle User Group, so which is also fantastic. Orapub was acquired by Viscosity earlier this year, which in Viscosity is a wonderful company. I've known them for many years. What Viscosity tries to do, right, and this is my interpretation, is they try and get value that is value from data that most people don't recognize is valuable. And this presentation is a good example of that. Most people don't know what sysmetric data is. Most DBAs don't use sysmetric data, but we are going to use sysmetric data to predict the next average active session value. That's value from data that is typically overlooked. So that's a perfect example. So Viscosity does all sorts of IT related services, Oracle, SQL Server, it goes many, many things. Viscosity also employs a number of Oracle ACEs. So I work with some really talented people, which are fantastic. I've known all of these people for many years now too. So my machine learning journey, it started back in 1987 when I discovered Turbo Prolog, the language Prolog, and I was amazed how I could give it information and then I could ask it questions about the information and it could respond to me. I was like, wow, it's learning. And I was hooked. I thought that was fantastic. One of the most amazing things that I think I did was in 1990, I wrote a tic-tac-toe program to learn as it played. I then had it play itself, so it got better and better very quickly. And it worked. It was amazing. I didn't realize this, but what that is now called reinforcement learning. It's an aspect of machine learning, which is very powerful. And some of the things that we're going to talk about today, specifically neural network, reinforcement learning sometimes uses. So I didn't realize this, but in 1990, I was doing, which is one of the most powerful predictive algorithms available today. It's just, I'm still amazed by that. In 97, I started working with neural networks, and I did a presentation at the Rocky Mountain Oracle User Group. That's what that is, way back in 2001. And in 2007, I wrote my forecasting book, and now I teach a couple of machine learning classes. And the next offering begins, I think it's October, is my machine learning 1, and my machine learning 2 will be in December. So if you're interested, just check that out. From a business perspective, and this is important when you talk to people about machine learning, ask the question, what type of applications or what type of machine learning projects have you actually deployed the machine learning in a production environment? So for me personally, I have done quite a bit of work with internet marketing. And that is using machine learning to identify like the hot leads, the top leads that are most likely to buy from a specific promotion. And it works. It's shocking how well it works. The other thing, which relates more to what we're talking about today, is in IT operations. And that has to do with performance prediction. And this is one of the big use cases that I'll touch on just in a couple of minutes. So those are the areas that I've focused on machine learning. Here's an outline of the things I'm going to talk about, but let's just start talking about it. Number one, use cases. I like to start these type of presentations talking about use cases because you will be asked, why are you spending time learning about machine learning when you're a DBA? or you're a developer, right? Sometimes people are like, well, that's not what you do. You're not a data scientist. Well, we know about Oracle, which gives us domain expertise. And so one of the most obvious use cases in our work is to answer the question, I'm learning about machine learning because we need better monitoring and alerting. Machine learning can go way beyond rules and statistics. So you can then scale, monitor more systems, and monitor them better using machine learning. So that is the most obvious use case if you're involved with, if you have access to Oracle data. Okay, and so that's what we will be doing today. Okay. So what we're going to be doing is what's called a supervised learning model. Okay, and the reason it's called supervised is because the data we will give the algorithm to produce the model, we are going to give the algorithm both the attributes of performance, think of it as the input data. We are also going to tell it what the prediction, what the actual prediction is or should be. For example, if we have attributes of performance, and how was performance? Well, we could label it as bad or good or green or red. Okay? That's called the label. So what we're trying to do is to teach the algorithm when it sees this pattern of performance attributes, performance was bad or good. Okay? And if we give the algorithm enough examples of this, enough samples of this, it will slowly learn to recognize the patterns and associate this pattern. Let's say this is one snapshot of sysmetric data with poor performance. Now, today, we are not going to be predicting like green, yellow, red, bad performance, good performance. We're actually going to predict the future average active session value. So we will not be doing the red and green. We will be doing the actual value. What will be the next average active session? And it's called a supervised learning model or algorithm because we train the algorithm, right? Or we train the model. The algorithm trains the model, right? Because we give the algorithm both the inputs, the attributes of performance, and we tell it the answer. Like, this is the value of the next average active session. Now, the type of algorithm that we will be using is called a deep learning neural network. And we'll talk about that like right now. Okay. Oh, Victor asked a while ago. Sorry, I missed that, Victor. Yes, I'm going to share the Colab project. In fact, it's on my website right now. Okay. Yeah, everything I'm going to do, you will be able to do today. And you can experiment and yeah, and I'll show you how to, what knobs you can turn and all that. Okay, first of all, neural networks are based on truly our feeble and weak understanding of how our brains work. Okay. The artificial neurons, which are put together in a network, that the first paper that I'm aware of was written in 1943. Okay. So this is not brand new. That's the first thing I want to tell you. Okay. First thing, our brains are incredible, and our attempt to create an algorithm and a model that somehow works like our brain is feeble. I don't know how else to say that respectfully. But it is truly amazing what we can do with artificial neural networks. Okay. So let's say this is a neuron right here. So what happens is these artificial or actual, well, let's say artificial, it receives inputs, and the inputs, you can think of it, they're from some sensor, like eyes, ears, or touch, or AWR data, Oracle performance data. Okay, we take these inputs, we give it to this neuron, and what it does, the neuron like sums up the energy that it receives, and then it will output energy to all of the neurons that it's connected to. And so there's this kind of flow of energy. Okay. And when that energy flows through the neuron, it's called, it fires. And sometimes if you've seen an animation of the brain, you'll see these flashes. Those are the neurons firing and sending out energy to the other neurons that they are connected to. Okay. Now, giving enough input data and given enough neurons, learning actually occurs. And it's quite amazing to see this take place. So you may be wondering, well, how many neurons are in like living creatures? Well, I have a table to show you in the next slide, but just in summary here, us humans, we have about 86 billion neurons, right? That's a lot. Cats have about 750 million. Dogs, 2.25 billion. And sea squirts have 231. Sponges, the actual, living sponges, they have 0, no neurons. Okay. All right. By the way, there are neurons, they don't just reside in our brain. They are cells, right? And they live in, there are different types of neurons in different areas of our body. Okay. Now, I also want to mention it's important that the learning that we are doing today in our project, it's driven, it's purposeful. It's driven by the code that we write and the given objectives. This is not random or something just, emerges. It's not what we're talking about here. It's very driven with very specific objectives. Okay. However, there is randomness in this process. And this is important to understand. Okay. Neural networks are so good at remembering that they tend to memorize the data that we give it with incredible accuracy. Okay, that's bad. You may think, oh, that's great. Well, no, because we don't want the machine to memorize. Okay? If it memorized, then let's just use a database with a select statement, right? The beauty of machine learning is it generalizes the patterns. So when input is given that it's never seen the exact input, it kind of looks at it and says, well, I've never seen that exact input, but I've seen input similar. And in those cases, performance was bad. So I'm going to predict performance is going to be bad. See, that's the beauty of generalizing the pattern. And that's what we want really any machine learning algorithm to do, is to create a model that can generalize. Okay? What we do to make it more difficult for the neural network to memorize and to force it to generalize pattern recognition, we actually disable some of the neurons. It sounds crazy, but that's what we do. And there's a special term or word for that called regularization. And you will see that in the machine learning code that I will show you when we do the project. Okay. Now, also, these artificial neural networks, they're typically, and conceptually, this is good to think of it like this. They're organized in layers. Okay, it's like we have the input, we have a layer, 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 and we have output. And so like the energy kind of flows through left to right or right to left, whatever. Okay. But they're organized in layers. So you will, I will talk more about this, and you will see this when we look at the actual Python code. Okay. So I mention this because multiple layers in the neural network is nothing new. Okay. When you hear the word deep learning, that is not about multiple layers. That has been around since like 1943 kind of a thing. Okay. All right. Next slide. So this is a reference. I think this is very fascinating. This is the URL at the bottom. If you want a larger list of animals with how many neurons there are. It's amazing. I love this. An ant. 250,000 neurons. Just to give you some perspective, typically the number of artificial neurons we use is going to be less than 100. Okay. And one of the reasons we don't have very many neurons is it takes a long time for the algorithm to learn the patterns to create a model that performs well. And this will make more sense as we get into it. Now, if you're fascinated with the biology or our attempt to understand cells and neurons, this is a new book. It was released this year, called The Secret Language of Cells. It talks about, in part, how neurons have different ways to communicate with each other. When I said this, like flash of energy, well, yes, they can use electricity to communicate. They can use chemicals to communicate, and there's other ways that they can communicate. It's just fascinating. So there is one specific chapter in this book about neurons. So there you go. Okay, multiple layers. Okay, on the left, that is the input, the X's. Okay, think of those as input from our eyes, from our ears, sensory. But you can also think it as one snapshot of sysmetric data. So X1 may be like the value of average active sessions. X2 could be database time per second. Right? X3 could be the number of logical reads that occurred or per second. Okay, and so these inputs for every one of the sysmetric samples, right? Like AWR snapshots, like once every hour, we're going to have another sample set of sysmetric data. So each row, okay, I scratched the row right now. So each snapshot data of sysmetric data we put into the network, and it flows from one layer to the next. Okay. So you see, okay, well, first we have the input layer, and we have a number of hidden layers. They're called hidden layers. That's just what they're called. Okay. And then we have the output layer at the very end. So what's happening here is that if we're training our network, okay, we're going to give it, let's say, some sysmetric data for one snapshot. It works through the neural network, and it's going to give us an answer. In this case, the answer is going to be either green, performance is good, or red, performance is bad. Okay. And as the neural network learns, like we will tell it, hey, with this particular input, performance was really bad. Okay. And so when we give the input to the network, if the network says, our performance is going to be good, we're like, no, that's wrong. And so these connections here have different knobs you can turn and adjust them. And the algorithm will start adjusting these knobs until with a specific input, it gets the correct answer. Okay, once it does, okay, we give like another sysmetric data sample. We put that into the input, and we see what the prediction is. If the prediction is correct, then we go on to the next sysmetric sample. And if the prediction is wrong, we have to adjust. The knobs until it gets the right answer. The problem is, if we adjust the knobs, that could mess up the correct predictions that it is already making. So we have to start all over again with our first sample. And so you go through this iterative process with turning all the knobs until the outputs are correct for all the given inputs. And this can take a long time, minutes, hours, days, if it's huge. Usually for our type of work, it would take a few hours to train. Okay, now let's talk about these connections, because that gives us insight into simple neural networks as well as more advanced neural networks. Okay, so what we're looking at is a diagram, and the circle here near the top, okay, that is supposed to be the neuron. And you see the X1, X2, X3, okay, that's like output from a sensor or from another neuron. Okay, so that data comes in. Each one of the like streams of energy is multiplied by a weight. The weight is one of the knobs that can be adjusted. The algorithm can adjust that knob. Okay, so the input, all the inputs are multiplied by their own weight, their associated weight, and then that's all summed up. It just gets added up, okay? And that's what this is all about here in the circle. But we're not done yet. All that output goes into what's called an activation function. And that's what's in the box here on the right. That's the activation function. And that then finally determines what goes out of the neuron, which could connect to many, many other neurons. So when we look at a network of neurons, each one of these connections has an associated weight. So when you get to a larger network, every one of these connections has a weight that the algorithm can adjust. Yeah. So this is why when you have a large network, it can take a long time to train the model, because there's so many knobs that can be turned. Yeah. Okay. You guys good? Everybody good? Somebody chat in. I'm good. So I know somebody's still out there. All right. Fantastic. All right. Okay. Now let's talk more specifically about deep learning. Okay. The networks, the neural networks that I have been talking about so far are commonly called multi-layer. That makes sense. Perceptron, that's a cool word. All right. Multi-perceptron, or MLP, you will hear, artificial neural networks. Okay. Now these have been around for many, many years. Okay. When we get to deep learning, the neurons are not typically called neurons, okay, or artificial neurons. These scientists feel like they can call them a cell, which is like, okay, but hopefully, anyways, they call them a cell. So you'll typically hear the word cell. Now, why do they give it so much like glory and call it a cell? Well, it's because they're more complex than what I just described. There's logic. There's like gates. So if you know anything about transistors and integrated circuits and logic gates and that kind of thing, think of it like that. There's actually logic in every one of the neurons, artificial neurons. It's not just a simple, I'm going to sum up the information, pass it through an activation function. It's much more than that. Okay. And different type of deep learning networks have a different architecture in the cells and how they work together. Okay. All right. Those layers that we talked about, there are different types that are layers that are specialized. See, I mentioned input, hidden, and output, but there are other layers as well. So be aware of that. Okay. The classic deep learning model is called a recurrent neural network. Okay. The word recurrent is key to understanding this. The networks that I've shown you, everything just kind of flows like left to right, all the energy. Well, what recurrent neural networks can do, they have feedback. So like the output from one, if this is a neuron, the output can actually be fed back into it. The output actually can go down to the cells below it in the same layer. And who knows what, wherever else. The key is that it's not just simple left to right. Okay. And this gives like memory, right? It gives memory like, hey, what just happened is related to what's going to happen. It gives it some temporal or time understanding. Okay, so remember that. Okay. Okay, there's a couple words you need to know here. Keras, which sounds like a Klingon word, but that's just an API written in Python. Okay. The reason that API is written is because below it is really the serious linear algebra, matrixy number crunching, and that's done in software called TensorFlow, which you can directly work with TensorFlow, but Keras kind of sets on top of it and makes it much simpler for applied machine learning people like myself to actually use TensorFlow. So you will see this, you will notice these words in the Python code when I show that to you. TensorFlow, surprisingly, maybe not so surprising, it was written by Google and it was first released in 2015. Okay. So really, from a relative perspective, it's very recent. So deep learning is relatively new. Okay. All right, we have a couple more slides about deep learning. Okay. Many machine learning applications have to do with sequences. Just think a sequence of numbers, predicting the next number, something like that. Well, in many of these sequence applications, the patterns, the more recent patterns are just as important as the older patterns. For example, right? Knowing the history can actually be beneficial when predicting the future. And much of the data, especially that we use in the Oracle performance prediction, is called temporal data. In other words, if you think about, let's say we're charting average active sessions, and let's say the value that just occurred is up here, okay? And then the previous value was down here. And so this first value up here, it's related, it's up here in part because of what happened before. And what happened before is related to what happened before it. So there's this temporal time relation with the data. Okay, and this is called time series data. And it's important that we understand if we're using time series data, because some machine learning algorithms recognize this temporal or this time series data. They understand that, hey, this data, this point is related to that point, which is then related to that point. It's important that we know and understand if our model can absorb and understand that relationship. Okay. Some machine learning models do not recognize temporal relationships. A good example is a decision tree. which is essentially an index structure is what it is, okay? Which we're not talking about that today. So decision trees do not understand the temporal data. Okay? In fact, if we take the data and we shuffle it like a deck of cards, shuffle it, and we completely mess up the temporal relationship, the decision trees will work exactly the same. Right? But a deep learning neural network, it will not work the same, because by shuffling our data, we completely just obliterated the temporal relationships. They just don't exist then, even though in reality they do. Okay, so this is why, because of this recurrent and the feedback and the multiple layers, this is why recurrent neural networks have time series sequence capabilities. Okay, but they're not perfect. Okay? There are limitations. And so there are variants. There are different recurrent neural network algorithms. So to prevent the older patterns from kind of fading away. And two of the most populars are called this LSTM, which stands for long in the past, short-term memory artificial neural networks. And then there's another variant called gated recurrent unit artificial neural networks. The difference between these two is that the cells, remember the cells? The cells in GRU, deep learning networks, are simpler, but have similar characteristics in terms of their capabilities with the LSTM networks. This is important because if there's less code, if they're simpler, the algorithm will, in a sense, run faster and will train and build the model quicker. And that's one of the benefits. And I've actually tried, I've used both of these, and the GRUs do learn quicker, but I still use the LSTMs probably because there's more, I think there's like a larger community that uses them. That's probably why, but that's just me. All right, you also need to know what's called convolutional neural networks, or CNN. Okay, these are really good at recognizing, images. Like, this is a cat, that's a dog. That's a giant rock in the road, kind of a thing. So these are amazing. I've done some work with image recognition, and gosh, it is shocking how good and how easy it is to do some of this image recognition. Okay, that's a whole nother talk, another presentation, and it's really fun. It's pretty cool. It's amazing. I mean, it's kind of scary how well it actually works, right? All right, I think it's the last page here. All right. Okay, now, let's see. Yeah, there's additional and specialized gates, more logic within an LSTM cell. Okay, you can read that. Yeah, they're actually amazing at recognizing newer and older patterns. This is interesting. They're very popular for speech recognition, although probably less so. Well, no, speech recognition. Believe it or not, music creation. I actually did this just as a project on a weekend. What you can do, with the artificial neural network, you feed into it music from like a certain genre. You pick a genre, you get a bunch of music, and there are public libraries where you can get this. And you just basically feed this in to the neural network, and it kind of learns the patterns of that genre, that type of music. Okay. Once you feel like it's learned enough, then what you do is you give it like one input, like one bar of music, and then you play that. You play that, that one bar of music, like maybe just ding, like on a keyboard. And then you take that And then you put that back in as the input, and then it produces the next bar of music. Boom, and it plays that. And then you put that back. And you hear it will start creating the music. And it sounds kind of like the genre. It's shocking, but it works. Okay, that's just some of the crazy things that we can do with neural networks. All right. Okay. Let's see. Okay, that's really all I have to say about that. Okay. Now we're going to switch to the project, and I'm going to use. Well, let me just start up the project right now. Okay. You will be able to do exactly what I'm going to show you how to do. Hey, if you have any questions, go ahead and just type those in the chat, and I'll answer. Okay, so I'm going to start up Chrome here. It's a different user. I'll start it up on my other screen here. Here we go. So I'm going to start from the beginning here. So you have, since this is being recorded, you will be able to do, you can actually do everything that I'm going to do. So what you want to do, first of all, okay, you need a Gmail account. Okay, open up Chrome. Don't use another browser. Just make it easy. Open up Chrome, and then you're going to want to go to your Drive, right here. Okay, go to Google Drive. Now, what we're going to use what's called the Google Colab environment. It's free. Your machine learning environment is set up by Google for free. You don't have to do anything. And it runs all in the Google Cloud somewhere. Yeah, they know everything you're doing, every keystroke you probably type, but okay, maybe that's a fair exchange for you. It's fantastic for training and for teaching, though, because you can do what I'm going to do, and you do not need to create your own machine learning environment. Okay, if you do want to create your own machine learning environment on your desktop or laptop, at home, on the website, when you download this notebook, the Python code, there is also a text file, which is the setup instructions. And that will tell you how to set up a local machine learning environment on your desktop. It's very easy to do once you've done it once. Okay. All right. So what you're going to do is, in order for your browser to recognize our Python notebooks, okay, and I'll explain what I mean by that, is you need to add the extension for Colab. We call it Colab. So you go New, you go to More, and then you go Connect More Apps. Okay, now this is in the setup instructions. Okay, and then what you're going to search for Colab. So type COLAB, and you'll see Collaboratory. Click that. There you go. See, it's installed. And you click that, it installs it. Once it's installed, then the setup instructions tell you to create in your drive a directory called OraclePub. Okay, if you call it OraclePub, it makes things a lot easier. Okay, then also on my website, you download this file right here. Okay, the extension let me make that bigger for you. That IPYNB, that stands for Interactive Python Notebook. There you go. Okay, there's actually Python code in there that's marked up with comments and all that kind of thing. So I'm going to double click this, and I will make this big, and that's what it looks like. Now, let me give you a real quick primer about notebooks. Okay. Now, notebooks are nothing new. They've been around for years and years. Okay. All notebooks have the concept of what's called a cell. That's an unfortunate word, since I just talked about cells. It's different. Okay. You see this cell is highlighted. Now this cell is highlighted. See? Now this cell is highlighted. What is wonderful about notebooks is some cells can be code cells. Some cells can be like text. And if I double click the text cell, you can see kind of what it looks like underneath it. Now, every cell can be evaluated or run. Okay? One way to run a cell is you do Shift Enter, and all notebooks do this. So I go Shift Enter, boom, and it renders the text the way I want it. Okay. For a code cell, I can hit the Run button right here. Okay. I can actually also do a Shift Enter, and you can see it's running right now. See the little things going. Okay. By the way, it's creating the VM on the Oracle Cloud or the Google Cloud somewhere, and there's the details on the VM and 1.28 gigabytes of RAM, kind of thing. Okay. And so that's what you do. One of the beauties with notebooks is that you do not have to run like the entire notebook. You can run one cell at a time, which means you can develop code and you can mess with the code and rerun just a piece of the code. It's a wonderful way to actually learn and to develop as well. Okay. Oh, one more thing. Usually when you actually use the notebook, it's top down. It's important. If I forget to evaluate a cell that maybe contains a function or a variable is set, and that's needed further down in the notebook, and it references that variable and it's not set because the cell was not run, then an error will result. So I encountered that yesterday. I forgot to evaluate a cell. Okay, so I have comments in here. Okay, this is the first code cell. So if you're using Google Drive, which I am, make sure that's set to true. Okay, you're probably going to want to always have that true unless your machine learning environment is on your desktop. Okay, learning just means I'm going to give more output on some things that we're going to talk about. Okay, this development, you want that to be false. Only if you're Craig do you want that to be true. And if you look at some of the logic below, it will make sense. So I actually ran this. Everything's good. All right. What we're going to do here is I'm going to evaluate. There's nothing you need to change here. This is going to try and mount the Google Drive. It's also going to download some software that was not part of the Google Colab environment by default. Okay, usually everything you need is going to be there. Okay, now it's going to ask me for permission to connect to my Google Drive, and it does this. That's the email, and it needs me to authorize this, and then I will get an email almost immediately. Let's see if it pops over here. I got one earlier today because I tested this earlier in the morning. Okay, I guess it figures everything's good. So it's attempting to mount the drive, and it did. Okay, so we're good. Okay. All right, now just most of the really, I'll just say, most of the crazy coding, the Python stuff, is actually not in this notebook file. Okay, why not? Because the notebook becomes big, complicated, and it will be overwhelming to you. So what I've done is some of the core machine learning Python code I wrote and put in a different file. And that file resides right here. And so what this cell will do is it will go get that code and bring it in your local environment. But you don't have to look at it unless you want to. Okay? So that's what that's all about. So let me evaluate the cell. And it should say, wait, is there output already? Hold on. No, there's not. Okay. It's working really fast. Yeah, not working in a local environment. It's getting the file. And then I imported it. This is what this, it's importing the Python file. And then just to make sure everything is working well, I actually reload it. I basically import it again, is what I'm doing. And this says reloading the Python library. It's done. So everything's good. Okay. All right. Okay, so let's see. These are a couple of the core Python libraries. Okay, pandas deals with what's called, or the functions in this particular library deal mainly with what is called data frames. Data frames to me is just like a relational table. Okay, so I'm very comfortable working in pandas. NumPy, sometimes NumPy, but NumPy for Python, that's numeric Python. That's where the serious number crunching will occur, except for the deep learning stuff in that library. That library does, matrices and linear algebra type stuff, arrays, any really deep number crunching stuff will be in that particular library. So let me evaluate that. Okay, loading the libraries and done. It's nice and fast today. Okay, so now we're going to get into the actual machine learning stuff. Okay, you'll notice how I'm using the notebook instead of PowerPoint slides. I love it because we'll be able to like run or execute, evaluate, the notebook. So this is like a living tutorial. So it's a lot of fun. Now it's time for a break. Okay, we started late and you guys probably need to take a break. So I'm going to keep my screen up. I'm not going to turn anything off, but let's take a 5-minute break. So I'm going to get my watch here, set a timer for 5 minutes. Here we go. All right, I will see you in 5 minutes. Okay, and we'll continue on. We have over 3 minutes until I start again. Oh, I recognize some of the names. Yeah, Luis. I think I've met some of you before. Hans, So, Buenos Aires. Can't wait to travel some more. Yeah. Poland, fantastic. Wow, we have full worldwide here. Nobody is in Australia or New Zealand, though. Yeah, oh, that's good. Okay, 1 more minute. Okay. Almost ready. Okay. Okay. Let's continue now for part 2. Again, if you have any questions, just type those in. Thank you, Marcelo. I'm glad you are waiting for me. It's nice when I get some kind of feedback because I just talk into a camera and I don't even know if you're really there. So, okay. So now before we can actually do the predictions, I want to teach you about some of the core topics that you need to know about to do any kind of machine learning work. Okay. There are other topics you need to know about that I will not discuss, but these are the ones that we have time to talk about today. So the first thing is, okay, when we get data, sysmetric data from Oracle, it will be normalized, right? Right. We have for each snapshot, right? I mean, it's an Oracle table, so it's normalized. So we have all the columns in the table, right? Average active sessions, database time per second, all that kind of thing. Well, you cannot give normalized data to a machine learning algorithm. Okay, it will not accept that. What it needs is for the entire snapshot, let's say just the sysmetric data, it needs all of that sysmetric data on one long row for that snapshot. So let's say the snapshot is at 9 in the morning, then there will be one row for, the date and time. Then there will be a column for the date and time. There will be a column for average active session, right? For database time per second. And so the data that we read in through a select statement or through a CSV file will need to be denormalized or pivoted. So every row will contain the data and we give to the algorithm like one row at a time. Okay, so that's important, first of all, because that will be confusing to you. Now, each of these rows will have information so that the rows contain information about the attributes of performance or the attributes of Oracle database activity. Okay. These attributes in machine learning terms, we call this the features. They are features of performance, attributes of performance. Okay. So you will hear the words features all the time in machine learning. When you hear the word feature, think of column. Think of column and a denormalized table. Okay. Now, the features are the inputs because they're the attributes of performance. Well, what about what we're predicting? What about the future? Okay, that's called the label, or sometimes called the target. Now, for our situation, if this is like time at 9 o'clock and we want to predict what's going to happen by 10 o'clock, that data is actually going to be in the next row below. That will be in the average active session in the next row. Okay, but the label information is available to us within the features. We just have to, in a sense, create or derive the label. So the features are the attributes of performance. The label is what we want our model to predict. So when we give it a particular set of features, attributes, it recognizes that pattern and says, oh, I know the label associated with this pattern. Its performance is good or performance is bad, something like that. So you have the label and the features. Okay. Now these are within Python. What we will do is we will take that CSV file, we will denormalize it. We will then we will create an array just for the features, and then we will create an array just for the label, which will be a numeric prediction is what we're going to be doing. Okay, I'm hoping that makes sense. So that's features and labels. Okay, now time series prediction is more complicated than your typical machine learning situation where you have data that is not related to each other. There's no temporal relationship. So if you think about time series, in essence, it's like a sequence, like this sequence of numbers here, 0, 1, 1, 2, 3, 5, 8. Okay, so let's just suppose that the above numbers represent a sequence of average active sessions over like a 15 minutes time span. So like every couple of minutes, there's another average active session value that's produced. Okay, so if we look at the first series above, which is this one right here, the short one. Okay, if the current average active session value is 2, right, and we give the model this sequence to learn, what would the model predict the next value to be? Okay, so, and this is not a trick question. Okay, give me this sequence. If we give this to the algorithm, it produces a predictive model. We would hope that if the current value is 2, the model would say, hey, the next value would be a 3, because that's the next in the sequence going left to right. Okay, that's nothing, there's no trick here. Okay, and the model will be, any model should be able to figure that one out. Okay, all right, well, any time series sensitive or time series aware model would be able to do that. But look at the second sequence though. Okay, if the current average active session value is 2, what would the next value be? Let's take a look at that. What would the next value be? It's not so simple, is it? No, because here, if the value is 2, then the next value is a 1. So the model would want to say 1. However, here's another 2, and the next value is 3. So the model may also want to say 3. Oh, here's another 2, and the next value there is a 3. So the model could say 1 or 3, or maybe something in the middle. You see, there's a problem there. There's a challenge there for the model to actually predict the correct next number. Now, there's ways that we can give the model more information about the history, right? Or if the model is temporal aware, it may realize that, hey, there's a 0, a 1, and a 2, And when I see that pattern, then I know the number should be a 1 based upon the data. Okay. But if the model says, well, okay, the current value is a 2, but I can look backwards and see 1 and a 2. It's like, oh, I've seen the 2, 1, 2 pattern. So the answer is going to be 3. So you can see how knowing the past and having the algorithm to be temporal aware can be very powerful when we're predicting sequences. Okay. Now, what I just showed you, this is called univariate data. It's like one column, say just a sequence of average active sessions. Okay. We never deal with data that simple. Sorry. Okay. We always have multiple columns, multiple features. Okay. And so we call that, surprise, multivariate data. So let's talk about this. Now, a little bit more about features. Whoops. See, I need to evaluate that. There we go. I double clicked it. That's what I did. So the inputs or attributes are called features. And we use, if you look at Python code, usually they're stored in an array. It's a capital X. And the label data is stored in an array with a lowercase y. Okay, that's just the way it is. So don't fight it. You can't change it. That's just the way it is. So just be aware when you look at Python. Okay. Okay. Now, okay. What I'm actually going to talk. I'm going to what I wrote here. I'm going to talk through that with you. So I'm going to evaluate. Here's some Python code. We're going to use this. I'm going to evaluate that, and let's look at the output right here. Oh, I need to show you just a little bit of Python right here. You see this X dot shape. Okay, X is the array that we created. That NP is that numeric Python. All right, we're creating a numeric Python array, and that's the array. And you can see we have 6 rows, and there's 4 columns. And this command, I get X, this is the array, dot, well, what's the shape of the array? And that will actually should be, the output of that is 6, 4. I have 6 rows and 6 columns. So I use the shape a lot to check to make sure what I think the data is physically is, the reality. So I use that shape a lot. Okay, so okay, now let's make this a little bigger. Whew, that's like really big. There we go. Okay, so looking at this array, okay, let's say this first column represents average active sessions, and the second and third and fourth column represent something else. Database time per second, logical IOs per second, something like that. Okay. So let's say I'm looking at the highlighted row that starts with the 3. So the average active session is 3. Okay. What is the next, based on my data, what is the next average active session value? Okay. Looking at this, using this array, focusing on this row, what is the next average active session value? It will be 5. That's what the data tells me. The first column is average active sessions. So if I'm looking at this data, the next average active session is 5. Okay. If I look at this row, the next average active session, based on like historical data here that we collect, let's say this is sysmetric data, then the next average active session value would be a 7. Okay, so you can see it's below. This is all historical data. Okay, couple things. What's the next value? What's the next average active session value for the last row in the array? Well, we don't know because it hasn't happened yet, right? That's what just happened. We don't know what's going to happen. In fact, this data, the 11, 22, 33, 22, That's what we give our model to answer the question, what's going to happen next, right? Because it doesn't know for sure, but it's going to make a prediction for us. The data before that is historical data, and we actually know the answer. Okay. It's one thing I want you to understand. Now, it's important. The machine learning algorithm expects, remember like that row of data? Okay, it expects the features, the attributes of performance, and the label to be like at the same row number. Okay, so if this is the feature data, the label, what happens next, right? The next average active session, that's going to be a 3. So when we look at the label array, okay, what's associated with this guy right here? It's going to be the number 3. Okay, and so what is going to happen is once we've kind of cleaned this up properly, so this is like the first row, that's the first label. That's the correct answer, right? That's the first row, first label. Let's look at this one right here. This is the third one, and that should be a 7. Well, is it 7? If this is the row, yep, 7 is what in reality, that's the historical data, right? So what we're trying to do is we give this to the algorithm and we say, these are the attributes. When you see that, you need to learn how to say 3. When you see this, you need to learn how to say 5. And we will give it as many, we'll just let it learn. Say, it just practice until it can get all these correct. Okay, so this will be our feature data, and this will be our label data. Okay, now, so, all right, notice our feature data, we excluded this last row, right? Because we do not have a label, because we don't know what the label will be. We are going to predict it, but we don't know. So we will not train the model with this data because we do not have an associated label yet, but we will. Okay. Okay. I wish I could see your faces so I could tell if that makes sense. That's actually very key to what we're doing now. Okay. Okay, next, we need to talk about scaling. Scaling is something like you just do usually, but why? Okay, well, most machine learning algorithms, they struggle with producing good performing models when the data is not scaled. Okay, why? Okay, let me give you an example here. Most models, they will consider, and this is just one example, that they will consider larger values to be more important than smaller values. Ooh, see, it's biased. We don't want that. So let's say you have a data set that has like huge numbers and very small numbers. Yeah. It's just not, it's not going to work. Okay. So, and you have, some data is maybe in inches, some in centimeters, kilometers, miles, all that kind of stuff. So we need to scale the data, and there's many ways to scale, different types of scaling. But what we're going to do is that we're going to scale using what's called standardization. Okay. So what we're going to do, and this happens feature by feature, they're independently. So like one column, one feature, say average active sessions. We're going to give it like all the average active sessions, and the scaling algorithm will find the minimum value, and that will be transformed into a 0. The largest average active session will now become 1, and everything else will be proportionally adjusted, proportionally transformed. And so all the values for each of our features will be between 0 and 1. And now the algorithm looks at the data and it's like, oh, it's scaled. Thank you. You know, some algorithms will throw an error if the data is not scaled. Some will simply just perform poorly. Some will give you a warning that says, hey, it appears your data is not scaled. And that's not really good. So it just depends. So let's actually take a look and see how this actually well, not how it works, but how the data changes. So I'm going to evaluate this cell. Okay. So what we did is I actually loaded some data that's used a lot in tutorials and just for, you know, small research projects. It's data about irises, like the flowers irises. And so I just loaded that data right here. Okay. So this is the original. This is some, here we go. Let me go up here. Okay. This is before any scaling occurred. So I'm just showing the first 5 rows, and these are the features or the columns right here. Okay. And I don't even know how to say that. Can I just say sepal? Can I say sepal or sepal? There's the length, the width, the petal length, and the petal width. Okay. So this is unscaled data right here. Okay. And so if I look at some basic statistics, so for the sepal length, which is the data right above it here, okay, I have 150 rows, and thankfully, it just makes sense. The other columns also have 150 values. And this is the average, the mean, standard deviation, and the minimum, some percentiles, and then the max right here. So this is unscaled data. Once I actually run this through the scaling, so I'm calling the scaling function right here with the min and a max 0 to 1. You can change that. You can have a minimum of -10 and a max of +10 if you want it. It will scale it to whatever you want. But we are scaling 0 to 1. After the scaling, notice these numbers look very different now. Okay. And if you look at the descriptive statistics, we still have 150 values for the sepal length. But notice the minimum is 0. And of all of our values, the maximum is 1. Now notice all of the features right here have a minimum of 0, and they all have a maximum of 1. But because all the other values, besides the low value and the high value, they're all proportionally transformed, you'll notice that the means are different, right? And the standard deviation is going to be different as well as the percentiles. But the minimum is 0 and the maximum is 1. So it's scaled. So this is just something that you do like all the time. Okay. Some people don't even think about it. They just scale the data. All right. Okay. Another thing we do, you can do this with any algorithm, any data set, if it's time series. Okay. What we're going to do is we're going to give the algorithm some historical data. Now, if you recall at the top of this notebook, when we looked at those first couple sequences, I was by not only just looking at the most recent value, but 2 values before, I could then make the correct prediction. We're doing the same kind of thing. So instead of me reading this, we're going to run some code, and you will visually understand this very, very quickly. Okay. So what we're going to do, I'm setting a variable called in steps. This is the number of steps. And this is the number of historical, the number of past samples or number of historical samples I want to add to each row. Okay. So let me show you what I'm talking about right here. Okay. Here we go. So there's the raw data, and I actually gave these like feature 1, feature 2, feature 3, that kind of thing. Okay. We're going to step twice. So what we're doing, in fact, don't even look at let's focus on this raw data. Okay. If we're looking at this data right here, so what are the 2 rows prior to this? So if we focus on 9, 18, 27, row 4 here, what's the 2 previous row features? Well, we have these guys right here. And so instead of just giving the algorithm 9, 18, 27, we're going to give it, right, not just 9, 18, 27, 18, we're going to give it 7, 14, 21, and 14, which is these guys right here. We're also going to give the algorithm, right, the sample features before that, which gives us the 5, 10, 15, and the 10. So instead of giving it what just happened, we're going to give it what happened before that, and then what happened before that. And so we're giving it more historical information. Models, algorithms love this. It makes a big difference. It helps it recognize patterns, especially when they're very complex. Now, there is something that we lose here. We actually lose data that we can give to the algorithm, because let's take like this first row right here, row 0. What's the previous feature data? There is none. And that's what this is all about right here. Right? There's no values there. So we cannot give an algorithm data that's empty. Right? It's going to say, there's no number there, Craig. I can't do that. It will either ignore it or it will error. Okay. So usually what we do is we get rid of any rows that have like no values in them. Okay. That's what's going on. And so when we actually look at it at the end, we only have 4 rows that we're going to give to the algorithm instead of the original 6. Okay. Okay, so that's called stepping. We're doing it historical data. So if we step twice, that means we have the original plus 1 prior step and another prior step. Okay, so it's like we have 3 sets of features when the step is set to 2. It gets a little confusing sometimes. Now, just so you know that for the deep learning algorithm, it will not accept data shaped like this. Okay, it expects it in a very specific shape, which is simple to do in Python, but it wants the data to look like this. That's what it wants. Okay, and it's called, you'll hear, if you read about this, you'll hear the word called, oh, it needs it in a 3D or 3-dimensional shape. Okay, just make whatever. Okay, the first I'll say the first dimension is the number of actual samples that we're going to give. Okay, we're actually going to give it 4 samples. Okay, here's the first one. Here's the second one. Okay, and then how many steps plus the original? Well, that should be 3, and you can see the steps, right? Like this is the 1, 2, 3, and they're all shaped like that. Okay, and then we'll fundamentally, how many features are we really talking about? 4. 1, 2, 3, 4. So what you do is in Python is we give, after we got rid of all these NaN values, we then have an array like this, which has 4 rows and 12 columns, and we reshape it into an array which has 4 samples, 2 steps plus the current, and then how many features. Okay, and you do that. It's really easy in Python. You use what's called where's the reshape right here. We're going to reshape that X array, and then these are the dimensions of the array right here. It's pretty cool. And boom, does it just like this. So be aware when you see some weird stuff like this going on, you just have to do it. That's the format. Or the deep learning algorithm will just say like, no, I'm not good with that. He'll just stop. All right. Okay. Feature selection. I think this is the last thing we're going to talk about before we get into the algorithm. Yeah, the build flow. Okay. One more thing we need to know about. So what's going to happen is, when we have all these historical steps and there are many other things that we can do to our data to make it easier for the algorithm to produce a good model. Okay, we can create, ratios, and we can take, data from 2 columns, do some math to create a ratio, and then you get rid of the original 2 columns. You can do that. Now, as a DBA, you're thinking, that sounds like, pretty harsh. Do we want to use ratios? Ratios are bad, right? No, okay. Not in machine learning. So we can derive new data from the existing data. Okay. We can do all sorts of crazy stuff. Okay. We can, anyway, it's like an endless things that we can do to the data to create additional features to help the hopes of helping the algorithm create a better model. Okay, this is called feature engineering. Okay, a DBA would call this derived data, and it can make a huge difference in the performance of your models. Okay, that's the great thing. The problem is though you can very quickly engineer literally thousands of features. Now, if you give the algorithm thousands of features and you have thousands of rows, it's going to take forever for that thing to create a model. And it's probably going to be a really bad predictor. Algorithms want the fewest numbers of powerful predictive features. Okay? It trains fast and it's good at making predictions. So the question then becomes, which features are the most powerful? So we've engineered thousands of features. Which ones are the best? Well, as you can imagine, there are some PhDs out there who focus on what's called feature selection. And there are a number of algorithms to select the best features. And so I have 2 of them that we can, well, actually there's a number of them I have built into the code. But for today, I'm going to show you just 2 of these. So I'm going to run this code right here real quick. Okay. By the way, feature selection can take minutes and minutes and minutes to select the best features, depending upon the feature selection algorithm and the amount of data that you have. So even in this project, we only do the feature selection once. So even when we get new data, like new data becomes available to make the next prediction, I do not go through the feature selection every time. It can take like 5 minutes every time. And that's not acceptable. Okay, so so here's the output from this. Okay, so there's 3 different algorithms that I use. Okay, we used it uses the random forest. These are decision trees. Think index. Okay, and I'm not going to talk about the specific algorithm, but it is telling me the petal length is your most powerful predictive feature, followed by petal width, and then the sepal length and width. Okay. Now you'll notice the numbers are 4, 3, 2, 1. So it's not giving me, well, like how much better is feature 1 compared to feature 2? It just says petal length is the best. Okay. So the chart is pretty much meaningless here. But looking at a different algorithm, this is using the F statistic. This is just another way to do feature selection. It said the petal width is the top. Up above, though, it said the petal length was the top. So they disagree, okay? But what's really nice about this is you see the difference. So really, if I look at this, I might say, you know what? Maybe it's better if I just use 2 features, and these are the 2 features I want to use. Instead of giving the algorithm all 4 features, just give them 2, which is half the amount of data. See, it could be significant. Okay. Now, is it really going to make a difference? Well, you're going to have to test it. Okay. All right. There's yet another way to do this. This is another algorithm that I just started testing out. It takes a while though for this thing to run. But the output of this, it does some statistics. And if it passes the test, it says, yep, that's a good predictor. That's a good predictor. These 2 are not good predictors. And so again, the top 2 are the petal length and the petal width. So what I typically do is I do different feature selection analysis, and you'll notice that most of them will give you like the top features will typically be pretty much the same. Okay? And what you do is you look for things like this. There's almost always some kind of a drop off, and then that's where you draw the line. Okay, but you're never going to know for sure until you test. This is very important, and this will be done in our project. Okay, we're going to be done at the top of the hour for sure. Okay, now we're going to have a function called the build flow. This is where we're going to build it. I'm going to build the algorithm here, or build the model. Okay, all right. So initially we loaded the data. The second thing we're going to do is that we are going to do some pre-processing. Pre-processing is where we engineer features, right? We do feature selection. We do all that stuff. Pre-processing happens after we load the data, but before we give the data to the algorithm. Okay, and that's a huge topic, and that's why we spent most of this second part here talking about pre-processing, scaling, right? Feature engineering, feature selection, that's all part of pre-processing. Okay. And I'm not going to go through the code here, but if you follow it, you can you'll recognize the things that I actually talked about. So first we load the data, then we do pre-processing. Okay. And then we're actually going to prepare to actually train the model. And this is like more technically called, we're going to fit the model. We're basically fitting the data with the algorithm to produce the model. Think of it like that. Okay, let's look at the deep learning stuff. Oh, by the way, here's the reshape. Got to get it in the proper shape. Remember that? That's where I did that. Okay, now you see the word TensorFlow. That's the underlining, that's the Google software. They know, you know that they know we're using their software. And then to make it simpler, we're going to have this API Keras, and we're going to load just one part of that library. We want the models, and the model that we want is going to be called sequential. Okay, now that's just how we structure this, but don't get all uptight about it. Just know that you need to actually load these libraries right here. Okay, what I want to show you, this is where we actually create the architecture, the structure of the neural network. Okay, now I'm starting to watch the time. I need to not talk so fast. I need to slow down. Okay, remember picture in your head, input layer, hidden layers, output layer. Okay, what I'm doing here is there's input, there's one hidden layer, and output. That's what we're creating right now. Okay, so this type of the structure of the model is sequential, one layer at a time. So we've kind of initialized our model right here. Okay, we're going to add a layer. Okay, well, what kind of layer? Well, we're going to add an LSTM layer, the long short-term memory neural network. Okay, now this is kind of confusing. I wish they hadn't done this, but this is the number of cells, right, in the first hidden layer. But the input layer, that it needs to know the shape. It needs to know. So it's like, what's unusual about this layer is that we're actually defining the input into the LSTM hidden layer, as well as the number of cells in the hidden layer. right? So we're defining the number of inputs as well as the number of cells in this first hidden layer, okay? All right, so we have the input, first hidden layer. Remember that regularization, we want to make it difficult for the neural network to memorize so that it will generalize its understanding of the patterns. We do this by adding what's called a dropout layer. And this will actually randomly disable some of the LSTM cells. Randomly. So no, we're going to turn you off. But it works. It works. So we can give it the percentage of cells that we want to disable. Okay, and that's a parameter that you'll get to set. And I usually do something like 20%. And you can change that, and you can see how it affects the learning of the neural network. Okay, so we have our input, got our input, our hidden layer, and then with that dense layer, it actually is going to mess with our hidden layer. And now we have to take all the output, and we have to and since we're going to add a dense layer, which means we're going to take all that hidden layer, we're going to go like into one value, which is the output, which is going to be the prediction. And so there's one value. That's what we're actually predicting right there. So that is the definition of the architecture of this neural network. Now, let's say you're saying, oh, that's not very much fun, Craig. That's just one hidden layer. Let's have two hidden layers. Like, okay, all right. So what you do is you uncomment this line and this line. So this will add another LSTM layer, and it will also have an associated dropout layer as well. Okay, but I put a comment in here that if you do have your two layers here, you need to set this to true. Okay, so if both lines are commented, all right, okay, what did I say? Both lines are commented, ensure the return sequences line above is false. Okay, but I uncommented them, so it needs to be true. Okay, otherwise you're going to get an error. Okay, in other words, we're taking the output from the LSTM layer, and we're gonna return that sequence to the next layer right here. Okay, but the final layer, the dense layer, right? It doesn't want a sequence. It's going to actually get a value out of it. It's just like a value. So we need to make sure the last one is set to false. So I'm going to keep this commented right now because it will train quicker, although it probably will not be as good of a predictor. Okay. Now, this is within a function. So if you change this, you must reevaluate the cell to create the function. Okay. Now what's happened, we've actually defined our model. Okay. And now we will compile it. So we have our model that's been defined. Now we're going to compile it. This is like creating a cursor in Oracle. It's basically like executable code when it's done. Okay. And here are some parameters that we're going to give it. That's all I will say. Okay. Once it's actually done compiling that, which actually is like really fast, then we will take our model and we will fit the model with our feature data and our label data. Okay. And the way neural networks train is an iterative process that I talked about at the very beginning. And that can take a while. Okay. And by the way, we do not want to shuffle our data because our neural network is aware of the temporal characteristics of our data. All right. All right. And then boom. So let me just build the function, and it said function defined. Everything looks good. Okay. This is where we want to be. Finally, now we're going to get that final chart. So we want to see the processing details. How many cycles? Maybe just 10. If you want to slow things down, just put a number there. That's how many seconds to sleep. We don't need to do that. Now, the top features, we want to use feature selection to create the top, let's say, 3 features. So we set that to none, and that will trigger the features being selected. But then the next time around, like when it gets new data and it wants to do the next prediction, then it will know the top features and it will not go through the feature selection algorithm again. Okay. If you don't want to do feature selection, and let's say that you decided these are the best 2 features and I only want 2, well, then just use those. You would just do this. Boom. Okay. Or as I want to do feature selection, I want to say none. And this is the comment in Python right there. So I want to have 3 features, which isn't very many. There are like over 140 sysmetric features. Okay, so we could have a lot if we wanted to. This is how many historical steps. We're going to do 5. Okay, and then the number of cells. Now you can set the number of cells for the hidden layers to be whatever you want, but to make it easy, okay, what I did, I just created this little formula that could be a good place to start. Okay, that dropout percentage, we're going to set that to 20. Okay, and when the model is being built, it's going to build the data with like a certain percentage of our data, and then it's going to test the model. Okay, and this is the test percent. So we're going to build the model with 70% of our data and and test with 30%. Okay, and I don't want to talk about patience, and I don't want to talk about that for right now. Okay, so that's only code below, but just so you can see, just so you know what's happening. First, we're going to load the data, the initial data. This is the data that we've had. That's in our AWR repository, and this is going to be a bunch of data, and I'm going to pull from a CSV file. Then, like as in reality, when new data becomes available, right, then we're going to do another prediction. Well, the new data is going to be pulled from this CSV file right here. And so that's when it's going to keep making predictions, right? It's basically doing the initial training on this data, and then it's going to get new data and make a prediction. But it is going to retrain every time it gets new data, okay? All right, so there's the loading of the data, and I don't think, load the initial data, load the new real-time data, okay? And then it's going to go into some pre-processing and all that kind of stuff. And finally, it's going to make a prediction. Okay. Let's just run it. Okay. All right. So let's run it right now. It's starting to run. Okay, it's loading. The data is being loaded onto your Google Drive and in the VM here. So it takes a little while longer to get it to load it the first time. Okay. The feature selection will take a couple minutes probably. Okay, so this is how many rows we initially loaded: 66, over 500,000 rows. Okay, but those were normalized. When we denormalize, we only have 4,190 rows. So you do the math. If each snap is 30 minutes, and we have over 4,000, that's how much data we have. You can just figure that out. Okay. Data pre-processing. You can see some of the oh, there's our feature selection. Okay. Well, we'll stop it. Once we'll get a chart here. Okay, I'm actually going to stop it so we can actually talk. So I'm going to click this. If that doesn't work when you click, you go real runtime, interrupt, boom, and that will stop it. Okay, so let's talk through this real quick, and then I'm going to let it run for a while so you can actually see it. Okay. Okay, so what do? We load our initial data. It tries to find it locally. It's not there. Finally, it's got to go to the URL and get it, and then it saves it. Okay, so that's the initial 662,000 rows. Okay, it seems like a lot. But then once we pivot or denormalize, we actually have just over 4,000 AWR snaps, right, of just the sysmetric data. And this is sysmetric summary data, by the way, right? Okay, so we have 162 features. It's a lot. It's good, good. Okay, now we're going to load the real-time data, which is kind of what we will cycle through. We're going to do some pre-processing. We're going to clean up the data. You always do some cleanup, and I'm not going to, go through that. We're going to do now we're going to do our feature selection analysis, and I think we want to just the top 3. So using this random forest regression, I don't want to get into all that, but using that, these are the ranking of of our features of the columns right here. Okay, and as an Oracle DBA, this might make sense why I would choose those. Okay, a lot of possibilities, right? So these are the best 3 according to that feature selection algorithm. Okay, database time per second is a big one. Now I'm actually doing the official scaling of our data. Got to scale it before I give it to the algorithm. We're adding these steps to historical data. All right. We're getting rid of any NaN rows, and then we're going to start training our model. So this is this is all of our data. How many rows? And this is all the steps, and then the features. And these are like this is the last 4 rows. As you can it's all number crunching, isn't it? This is the Lstm network right here. So we're gonna have 18 cells in the hidden layers. And here's just that just describes it. These are the number of what it means by number of parameters. Remember at the beginning, I talked about adjusting the weights, all the connections. That's how many weights there are that can be adjusted. And that's only with 18 cells, the hidden layer. A lot going on here, okay? All right, and then it kind of works through the data multiple times. It should get better. This is the loss. Think of the error, okay? It's getting better. Right? Oh, and now it's like it's not getting better anymore. And in fact, it got worse, and it said, okay, we're going to stop. It's not getting any better. Now, this was really fast, okay? That's because we only have 3 features, and we have 3 steps or something like that, okay? Okay, so it created the model, and now this was the last actual average active session, and now it's going to make the prediction. And so the prediction is 8.7. This is the next, okay? And so it's kind of strange because, see, this is, let's get it up here. This is what the prediction is. This is what just happened. See, we don't know what's going to happen next. That's going to be the next blue dot here, wherever that is. Hopefully it's right there. Hopefully our prediction is exactly what happened, but it won't be like that. So let's actually rerun this thing. But I need to change the parameters because I don't want to show all the details. Okay. And now these are the things that you can mess with. You can set your own features. You can change the number of features. You can say, I don't want any steps. Put 40 steps in there. Don't worry about it. Just try it. I do want to refresh the screen, so I just want a chart. I just want that. And let's just let it go for a while. Okay, let's actually run it. Okay, so it's going to go through the same thing it did before, but the data, it will find the data right away. So it's be a lot quicker. Okay. How we do? Oh, it's almost top of the hour. Okay, we're just about done. So while that's running, let me just finish off here. I've taken the entire time. Okay, so project details. That's what we're doing right now. Going deeper. Okay, you can go to my website, you log in. If you don't have a login, be a free member. Log in, go to tools and presentations, then presentations, and look for this presentation. You can download the notebook, all that stuff. Okay, I have a free, an e-course, 18 session e-course. It's Python code, raw Python code. You'll know within a couple sessions if this is something that you're interested in. Okay. I have classes, right? Online classes kind of like this, except it's different. This is more of a presentation, all that. There you go. And thank you guys. So let's take a look and see what's happening. Now you can see the predictions. See, that's our next prediction. That's what happened. Let's see what's going to happen next here. Okay, that was pretty good prediction. Pretty close. Now you'll say like, God, Craig, that's really bad. Yeah, it is really bad. But we have a crazy simple neural network, right? It just has one hidden layer that's not super big. We don't really have tons of data. And we really have not done all the pre-processing that we should do. But we have limited time, right? But this is enough to get you going so you can get going, all right? So that's it, what I have for the presentation. Thank you guys so much for being here. I hope you're really excited about this, and it opens up this whole new fascinating world of the things that you can do with applied machine learning. Okay, so thank you guys for being here so much. If you have any questions, I'll be happy to address those. Otherwise, that's going to be it. All right. I don't have anything else to say.
Okay, sounds great. A great presentation. I look for the samples on your website.
Fantastic. All right. Thank you all. It's my pleasure to be
Thank you,
with you.
Brian. Gracias a todos por estar acá. Nos vemos en otra presentación. Voy a parar la grabación. Okay, thank you.
Oh, thank you. Oh, thank you.
Looking forward for the next presentation.
Okay.